surface described by the function g of x and y. As a reminder, the idea behind a level curve is it represents a set of points in the two-dimensional xy plane where the surface is, well, level. That is, at a constant height or value. This corresponds to the intersection of a surface with a plane parallel to the xy plane, which has a constant z coordinate. A good analogy here is to imagine the function g as describing some terrain, and k represents the surface of a body of water. Where the water meets the terrain, what you might call the shoreline, is what we mean here by a level curve. As you vary the value of k, you vary the height of the water and get different shorelines, or level curves. Another way to think about this is if I recolor the surface based on the surface's z-coordinate, what you might call elevation, at any point, you can think of level curves as being all points of the surface that have the same given color. Now, there's one fact about level curves that I want you to pay close attention to here. That fact is that the gradient vector to a surface at any point on a level curve is always perpendicular to the level curve at that point. To put it another way, the direction of steepest ascent, or descent, at a point on a surface is always perpendicular to the level curve containing that point. If we take a step back for a moment, this should make some intuitive sense. If a ball is rolling down a steep hill, and you block the ball's path with a barrier placed perfectly perpendicular to it, the ball will stop and will neither roll to the right nor roll to the left, which means the barrier is perfectly level to the surface it's sitting on. So what does this tell us about our current problem? Well, since our constraint, g of x and y equals k, can be thought of as a level curve, this means that the gradient of g must be perpendicular to the constraint curve everywhere along it, because the constraint curve is a level curve of g. But wait, if you remember the surface I showed you earlier, the boundary curve of that surface didn't look very level, so why am I saying it's coming from a level curve? Actually, this is just a misunderstanding, but a forgivable one since we have so many things going on in this problem right now. The boundary curve of this surface is certainly not a level curve of this surface because it's not contained in a plane. But this original surface is not the surface I was referring to when saying this constraint curve was a level curve. Remember, we actually have two surfaces we're dealing with in this problem. The surface coming from the function f, which is the one for which we're interested in finding the max and min on its boundary, but we also have a separate surface coming from the function g, which appeared inside the constraint equation. And I'm saying this g surface has a level curve that gives us this elliptical constraint curve. I actually haven't shown you yet what the g surface looks like, so here it is. As you can see, one of its level curves, this one, gives us our elliptical constraint curve. So the constraint curve is a level curve of the g surface, but the surface we're really interested in finding the max and min on is the f surface, and a level curve of g doesn't have to be a level curve of f. In fact, f and g really don't need to have anything in common at all with each other. So just remember that f is the main surface we care about, and the g surface is just quietly in the background helping us to define the boundary of our f surface. But don't worry too much about picturing the g surface. For our purposes, its exact shape isn't that important. All I want you to take away for now is that the gradient vector of the function g, whatever it happens to look like, is perpendicular to the constraint curve at all points along it. But now let's take a look at the f function and its boundary curve. Remember, our goal here is to find some criterion or equation that indicates where on this boundary curve the f surface could have a max or a min. Just so we have something concrete to look at, let's say we're interested in finding a max. The logic is the same for a min. Based on examining the picture, it looks like this point right here is the surface's highest point on the boundary curve. Do you notice anything about it? Well, going off of what we know from single variable calculus, since we're considering a maximum that's sitting on a curve, that point must occur where the curve is flat. But if the boundary curve is flat at that point, then it must mean that the gradient vector of the f function is perpendicular to the curve at that point. That's what we observed about level curves earlier. But remember that this boundary curve really came about from a level curve of the g function, the equation g of x and y equals k. That means that the gradient of the g function is also perpendicular to the constraint curve at this point. So at this privileged maximum point, we find that f and g do have something in common with each other. Their gradients are both perpendicular to the constraint curve, which means they are parallel to each other in the xy plane. So at long last, we have found the criterion we were looking for. The maximum, or minimum, of a function f of x and y, subject to a constraint g of x and y equals k, must occur where the gradient of f is parallel to the gradient of g. Actually, there's one small change we can make to this statement that will make it more usable in solving a concrete problem. Remember that if two vectors are parallel, it means that one is a scalar multiple of the other. So another way we can express this criterion is to say that the gradient of f is equal to some constant scalar lambda times the gradient of g. This constant lambda, by the way, is called a Lagrange multiplier, which is where this technique gets its name.
Bumping up the complexity a bit, imagine instead a function with two inputs and one output. You might think of the input space as the xy plane, and the cost function as being graphed as a surface above it. Now, instead of asking about the slope of the function, you have to ask which direction should you step in this input space so as to decrease the output of the function most quickly. In other words, what's the downhill direction? And again, it's helpful to think of a ball rolling down that hill. Those of you familiar with multivariable calculus will know that the gradient of a function gives you the direction of steepest ascent. Basically, which direction should you step to increase the function most quickly? Naturally enough, taking the negative of that gradient gives you the direction to step that decreases the function most quickly. And even more than that, the length of this gradient vector is actually an indication for just how steep that steepest slope is. Now, if you're unfamiliar with multivariable calculus and you want to learn more, check out some of the work that I did for Khan Academy on the topic. Honestly though, all that matters for you and me right now is that in principle there exists a way to compute this vector. This vector that tells you what the downhill direction is and how steep it is. You'll be okay if that's all you know and you're not rock solid on the details. Because if you can get that, the algorithm for minimizing the function is to compute this gradient direction, then take a small step downhill, and just repeat that over and over. It's the same basic idea for a function that has 13,000 inputs instead of 2 inputs. Imagine organizing